What's the most valuable object you can possibly imagine? A priceless painting by Da Vinci? The entire collection of crown jewels in the Tower of London? A solid gold statue the size of a skyscraper? All of them, every treasure on Earth, are nothing more than worthless trinkets compared to a planet located 41 light-years away in the constellation of Cancri. It is a world that scientists believe may have a surface of graphite and a mantle made almost entirely of pure, solid diamond. Its name is 55 Cancri E, and based on that predicted composition, its estimated value is 26.9 nonillion. That's a 26 followed by 30 zeros. It's a number so fantastically large that it becomes almost meaningless, worth more than all the combined wealth that has ever existed on Earth, multiplied by trillions. It's the ultimate treasure chest. But this isn't just a story about cosmic riches. The reality of this planet is far stranger and far more terrifying than just a simple diamond world. It's a story about a bizarre and violent new class of planet that is forcing us to rethink the very rules of how worlds are made. A wobbling star. The story of 55. Cancri E begins not with a picture but with a wobble. The planet was first discovered back in 2004, but it wasn't found using the popular transit method, where you look for the dimming of a star's light. Instead, it was found using a clever and painstaking technique called the radial velocity method. Imagine a professional hammer thrower spinning around to launch their hammer. The hammer is small, but it's heavy and moving fast. As they spin, the hammer doesn't just circle them. Its weight pulls on them, causing the thrower themselves to wobble around a common center of gravity. The radial velocity method looks for this exact effect with stars. A star isn't perfectly stationary when it has planets orbiting it. The gravitational pull of the planet, even a small one, causes the massive star to wobble back and forth in a tiny, repeating cycle. We can't see this wobble directly from 41 light-years away, but we can detect it in the star's light. As the star wobbles towards us, its light waves are compressed, shifting them slightly towards the blue end of the spectrum, a blue shift. As it wobbles away from us, its light waves are stretched, shifting them towards the red end, a red shift. By measuring these tiny, periodic shifts in the star's light over many months and years, astronomers can deduce the presence of an unseen planet. The size of the wobble tells them the planet's minimum mass, and the time it takes to repeat tells them the planet's orbital period. Using this technique, a team of astronomers had been studying the star 55 Cancri for years. It's a sun-like star, part of a binary system with a red dwarf companion, and it's relatively close to us. By 2004, they had already found 3 giant planets orbiting it. But as they gathered more data, they noticed a new, very subtle wobble, one with a much faster period. After careful analysis, they announced the discovery of a 4th planet in the system, 55 Cancri E. The initial data was stunning. The planet's mass was calculated to be about 8 times the mass of Earth. This placed it in a fascinating category of exoplanets known as a super-Earth, a world that is significantly more massive and larger than Earth, but likely still rocky, and not a gas giant like Neptune or Jupiter. It was one of the first super-Earths ever discovered. But it was the orbit that was truly mind-boggling. 55. Cancri E orbits its star at a blistering speed, completing a full year in just 18 hours. It is incredibly close to its star, about 25 times closer than Mercury is to our Sun. This proximity means the planet is a torch world, tidally locked with one side perpetually facing its star in a state of eternal, scorching daylight, while the other side is locked in an endless, but still incredibly hot, night. The surface temperatures were predicted to be hot enough to melt metal. This was already one of the most extreme planets ever found, but the biggest surprise was yet to come, when scientists began to speculate on what this strange new world was actually made of. The Diamond Planet Hypothesis. For several years after its discovery, 55 Cancri A was thought to be a water world, a giant, rocky core surrounded by a thick, soupy atmosphere of supercritical water. But in 2012, a team of astronomers at Yale University, led by Niku Madhusudan, proposed a radical and spectacular new theory. They suggested that 55 Cancri A might not be a world of water or rock as we know it, but a world made primarily of carbon, with a thick mantle of pure diamond. This extraordinary hypothesis was based on a key clue found not in the planet, but in its parent star. Stars and the planets that orbit them are born from the same vast spinning cloud of interstellar gas and dust. This means that the chemical composition of a star is a very good indicator of the raw ingredients that were available to build the planets in that system. You can determine a star's composition using spectroscopy. By analyzing the barcode of absorption lines in its light, the key to the puzzle was the ratio of two of the most important elements for planet formation, carbon and oxygen. In our own solar system, our sun has significantly more oxygen than carbon. This is what's known as an oxygen-rich environment. When a planet like Earth formed in this environment, the abundant oxygen readily bonded with silicon to form silicon oxides, which then became the silicate rocks, like quartz and feldspar, that make up the vast majority of our planet's crust and mantle. But when the Yale team analyzed the light from the star 55 Cancri, they found what they believed to be the opposite. Their data suggested that the star was carbon-rich, meaning it had a carbon-to-oxygen ratio greater than 1. It had more carbon atoms than oxygen atoms. This might seem like a small chemical detail, but it would completely change the rules of planet formation. In a protoplanetary disk that is rich in carbon, the fundamental chemistry of rock building is turned on its head. There isn't enough oxygen to bond with all the silicon, so instead of forming silicate rocks, the silicon would primarily bond with carbon, forming minerals like silicon carbide, a tough abrasive material used on Earth to make sandpaper and car brakes. Any leftover carbon would be left in its pure form. Based on this, the team created a new model for the interior of 55 Cancri E. Their model predicted a structure of almost unimaginable wealth. At the center would be a massive iron core, similar to Earth's. Surrounding this core would be a thick layer of silicon carbide. And above that, making up at least a third of the planet's total mass, would be an enormous, planet-sized mantle of pure carbon. Now consider the immense pressures inside a planet that is 8 times more massive than Earth. The weight of all those overlying layers would crush this carbon mantle under pressures that are thousands of times greater than anything found deep inside our own planet. Under such extreme and sustained pressure, carbon does not remain as graphite or coal. It crystallizes into its most stable high-pressure form, diamond. The hypothesis suggested that 55 Cancri E could be a world with a mantle of solid diamond, many thousands of miles thick. The surface or crust would likely be a layer of graphite, the lower pressure form of carbon. The environment on such a world would be truly alien. The atmosphere would be thick and choking, likely dominated by carbon monoxide and carbon dioxide. Any water that might have been present during the planet's formation would have reacted with the abundant carbon to form hydrocarbons, meaning instead of rivers of water, the planet might have rivers of tar or oil flowing across its graphite plains. It was a stunning and revolutionary idea. The news flashed around the world. NASA had found a diamond planet. However, as is often the case in the fast-moving world of exoplanet research, the story didn't end there. Science is a self-correcting process. In the years that followed the 2012 announcement, other teams of astronomers conducted new, more detailed analyses of the star 55 Cancri's light. These subsequent studies, using different methods and more refined models, came to a different conclusion. They found that the star might not be as carbon-rich as the original study suggested. While its carbon-to-oxygen ratio is high, it is likely still less than 1, meaning oxygen is probably still the more abundant of the two elements. The authors of the original Diamond Planet paper have since acknowledged that, based on this new data, the pure carbon planet scenario is now less likely, though they maintain it's not entirely impossible. The sensational headline of a world made of solid diamond was likely an oversimplification. But the story was about to take another, even weirder turn, as new observations revealed the planet's true, terrifying nature. A world of two faces. While the diamond planet theory was being debated, other teams of astronomers were using different telescopes to study 55 Cancri E, trying to learn more about its atmosphere and surface. The most important of these was NASA's Spitzer Space Telescope, an incredibly powerful infrared observatory. Spitzer is essentially a heat-seeking telescope. It can measure the faint infrared radiation, heat, coming from distant objects, allowing astronomers to map their temperatures. Starting in 2013, a team used Spitzer to do something remarkable. They stared at the 55 Cancri system continuously for over 80 hours, watching as the planet 55 Cancri E completed several of its 18-hour orbits. By measuring the tiny changes in the total infrared light coming from the system as the planet moved around its star, disappearing behind it and re-emerging, they were able to create the first-ever thermal map of a rocky exoplanet. They mapped the weather on a super-Earth 41 light-years away. The results were spectacular and deeply strange. The thermal map confirmed that the planet is tidally locked, just as theory had predicted. There is a permanent day side and a permanent night side. The temperature extremes were even greater than expected. The day side was found to be a searing 4,200 degrees Fahrenheit, around 2,300 degrees Celsius. This is far hotter than the melting point of most rocks. The night side, while cooler, was still an unimaginable inferno at around 2,000 degrees Fahrenheit, 2,100 Celsius. But the most bizarre finding was the location of the hottest point on the planet. Logically, you would expect the hottest part of a tidally locked planet to be the substellar point, the spot directly underneath the star, where the sunlight is most intense. But Spitzer's map showed that the hottest point on 55 Cancri E was shifted significantly to the east. This was a huge puzzle that demanded a new explanation. What could possibly cause the hot spot to be shifted? The current leading theory is that 55 Cancri E must have a thick, dynamic atmosphere. This atmosphere, whipped around the planet by the extreme temperature differences, would create powerful, supersonic winds. These winds would drag the superheated gas from the day side around to the night side. This would explain two things at once. First, it would explain why the night side is still so incredibly hot. It's being constantly blasted with heat from the day side. Second, it would explain the shifted hotspot. The supersonic winds would be moving so fast that they would physically drag the hottest part of the atmosphere downstream to the east of the substellar point. This leads to a new and even more hellish picture of what 55 Cancri E is actually like. The surface of the day side is so incredibly hot that it's almost certainly not solid. It is a vast, bubbling global ocean of molten lava. The atmosphere immediately above this lava ocean is likely made of vaporized rock, a silicate atmosphere filled with a mist of minerals like silicon oxide. This creates a weather cycle that is almost impossible for us to comprehend. On the scorching day side, the lava ocean boils, and the rock on the surface turns directly into a gas, creating a thick, mineral-rich atmosphere. This superheated, vaporized rock atmosphere is then caught by the planet's ferocious winds and blasted around to the night side at thousands of miles per hour. As this vapor reaches the relative cool of the night side, it would condense back into liquid droplets. This would lead to a terrifying form of precipitation, a constant, global rain of molten lava. This lava would then likely flow across the surface of the night side, back towards the day side, where it would be superheated and vaporized all over again. It is a rock cycle, but instead of the slow geological process we know on Earth, it's a frantic, violent, and rapid weather system. 55 Cancri I is a world where the air is made of rock and the rain is made of lava, the legacy of a treasure. So where does this leave the diamond planet theory? Is it completely dead? Perhaps not entirely. While the idea of a planet made mostly of carbon is now seen as unlikely, some scientists argue that its interior could still hold incredible treasures. Even if the planet formed with a more Earth-like composition, a planet 8 times the mass of Earth would have pressures in its core and lower mantle that are millions of times greater than the pressure at the bottom of our oceans. Under these conditions, any carbon that is present deep inside the planet would almost certainly be squeezed into a crystalline diamond form. So, while 55 Cancri E may not be a pure diamond planet, it is almost certainly a diamond-rich planet, a world with a heart of diamond even if it's hidden beneath a hellish ocean of lava. This, of course, brings us back to that incredible price tag, 26.9 Nonillion. It's a fun thought experiment, a way to put the scale of this potential resource into human terms. But it's just that, a thought experiment. The logistical problem is obvious. The planet is 41 light-years away. That's about 240 trillion miles. Even if we could travel at the speed of our fastest-ever space probe, the Parker Solar Probe, it would take us over 115,000 years to get there. But the bigger issue is the economic problem. Let's pretend you could magically teleport this planet's diamond mantle back to Earth. You haven't just become rich, you have destroyed the very concept of wealth. The law of supply and demand is ruthless. The only reason diamonds are valuable is because they are rare. If you suddenly introduce a supply of diamonds that is trillions of times larger than all of Earth's known reserves, the price of diamonds would instantly collapse to zero. They would become a common industrial abrasive, a novelty building material worth less than gravel. The very act of obtaining this ultimate treasure would make it completely and utterly worthless. The real treasure of 55 Cancri A is not monetary, it is scientific. Its value lies in what it has taught us and what it continues to teach us about the universe. It was one of the first rocky super-Earths to be discovered and studied in such detail, giving us our first glimpse into this common but mysterious class of planet. It pushed our models of planet formation to the absolute limit, forcing us to consider entirely new types of planetary chemistry and to realize that not all solar systems are built from the same ingredients as our own. It's now a perfect laboratory for studying extreme atmospheres, tidal locking, and the geology of lava worlds, helping us to refine the very techniques we will use to study more Earth-like planets in the future. 55 Cancri E is a world of superlatives. It's a super-Earth on a super-short orbit. It's a tidally locked lava world with an atmosphere of vaporized rock and a potential heart of diamond. Whether it's the ultimate treasure chest or just one of the most hellish places in the galaxy, its existence teaches us a profound and humbling lesson. The universe is more creative, more diverse, and far, far stranger than we ever expected. The 8 planets in our own solar system represent just a tiny, perhaps even boring sample of what's possible. As we continue to discover more of these alien worlds, we are learning that the galaxy is filled with wonders that defy our imagination. And the real treasure is not the diamond, but the knowledge itself.